We start today's session on hidden Markov models. These hidden Markov models are, in a way, a specific model under your Markov model, which was dealt in yesterday's class, that is the previous session. So, whenever you study about Markov models, what did you understand? You were talking about steady state probability. You were relating it with time, and then you were talking about a stochastic matrix and the steady state equations. So whatever you were talking about states was all visible to you, and there was nothing like hidden at the background. Now here in this case, we are going to have certain features which are hidden at the background but still would influence our model. Okay, so what is a hidden Markov model? So it answers the following three questions. The main thing, the first and foremost, is evaluation. How much likely is that something observable will happen? That is what you can see with your eyes openly. In other words, what is the probability of an observation sequence? Now, in order to get along with this evaluation process, we use two algorithms which are known as the forward algorithm and backward algorithm. The second is decoding. What is the reason for observation that happened? Why did it happen and why did you see it? In other words, what is the most probable hidden states sequence when you have an observation sequence? So what are all the hidden states which are influencing the event which you have witnessed? Okay, that is decoding. Now for this we use an algorithm by the name Viterbi algorithm, right? Then the third one, learning. What can I learn from the observation data that I have on hand? In other words, how to create a HMM model or models from the observed data. For this, we use an algorithm known as Baum-Welch algorithm. Okay, so now I have actually mentioned four algorithms. Your forward algorithm, your backward pass algorithm, your Viterbi algorithm, and Baum-Welch algorithm. However, in class, we are now going to actually understand what is meant by a hidden Markov model and how to apply a Viterbi algorithm. And then we are going to discuss one paper, or rather published paper, how they have used it in image loss. That's the main essence of our class. Now, what are the basic parts of a hidden Markov model? Number one, hidden states. The observation states are the symbols. Transition from an initial state to initial hidden state probability distribution. Next, transition to the terminal state probability distribution. What is terminal state? In most cases, it is not discussed in a model because all the probability is equal to 1 in general use. That is, the maximum value is 1. Then, what is the state transition probability distribution? This is what yesterday you have seen in your transition probability matrix. That is what is meant by state transition probability distribution. Then state emission probability distribution. This is what you are going to see as new thing today. State emission probability distribution. Okay. Now let us go into the theory behind this. So let us take a very small example and then we will start discussing each thing one after the other. So as I have classified now, our HMM now, our HMM or hidden Markov model, you can split it into two main categories. One is the states that you are going to have under the model. The other is the probability related issue. So under probability, what are you going to have? And under states, what are you going to have? Under states, in the earlier case, you had only transition state. Here, you are going to have one is hidden state, the other one is observable. Observable is what you see as output. Hidden is what is happening at the background. Now, very simple example is when you work with your systems, you say no. At backend, what do you use at backend here? At backend, I use Access. In front end, I use C++ or VC++. So these are all certain things where you will be using so that you can use your library files along with the features of your backend programming techniques. So this is also somewhat like that. So under probability, what are all the types? You will be talking about your transition probability. This is what you learned in your Markov model. Then you will be talking about emission probability. This is something new which you're going to learn today. Then number 3 is your initial probability. This also you saw yesterday, that is your P naught. Right. Now, how am I going to talk about this in detail? What I'm going to do is, we are going to take a very simple example. Say maybe we are going to categorize whether the day is sunny, rainy or cloudy based upon what a person is wearing. Say suppose we are inside and we do not know the outside condition that is prevailing outside. So what happens and how do I judge? I want to know whether it is going to be sunny or whether it is going to be rainy or I want to know whether it is going to be cloudy. But what am I seeing? I'm just having a person who's entering from outside and I am able to see what he is wearing. Whether he is wearing a shorts or a coat or an umbrella. Okay, so based on this, I want to judge what is the weather outside. So what is your hidden state here? Your hidden state is sunny, rainy, cloudy. Now, what is your visibility or your observable state? What the person is wearing, that is shorts, coats, or umbrellas. I'm going to go for this. And how do we actually understand this procedure? So, let us first see what happens when this is done. We will have 3 hidden states. As we see, we do not know what the hidden states are. So let us take them as x1, x2 and x3. And some x1, we see somebody who is wearing a coat. In the second state also we see somebody who is wearing a coat. In the third state, we see somebody coming with an umbrella. So now based on this, I have to decide. So how am I going to decide? Now these 3 states which are given here, okay, these 3 states which are given, these are my observable states. These are my observable states. Now these 3 states which are at the background, they are my hidden states. These are my hidden states. It's the emission that we are going to do. The emit, what happens and what is the evidence. Okay, so this is emission of evidence. Let us suppose, let us assume we have 3 hidden sunny, rainy, cloudy, and for all the 3 hidden states, we are going to have 3 outputs. That is wearing shorts. What is the probability that a man wears shorts on a sunny day? He wears a coat on a sunny day, and he wears an umbrella on a sunny day. Okay? So how do I represent? I will have shorts. So I represent as 0.6, and he wears a coat. The probability for that is 0.3, and he has an umbrella. The probability that he carries an umbrella is 0.1. So these are the three probabilities. On a rainy day, probability of wearing shorts is 0.6. His probability of wearing a coat is 0.3. His probability of wearing an umbrella is, let us say we will change this probability maybe. Your shorts is 0.3, so here it will be 0.65 is that he carries an umbrella. Similarly, what is given for a cloudy day? On a cloudy day, him wearing a shorts is 0. He doesn't wear a shorts on cloudy day. Let us assume that he does not wear shorts at all.
Excuse me, Lavanya ma'am, can you hear me?
10. He is going to have a coat with 0.5 probability of wearing a coat, and again 0.5 probability, because it is cloudy, he may carry an umbrella.
Hello. Lavanya ma'am, can you hear me?
Yes, he wears a shirt or a coat or an umbrella. Here it is 0.3, 0.6, 0.1, it is 1. Similarly, for rainy day, it is 0.5 plus 0.3, 0.05 plus 0.3, 0.35 plus 0.65, which is 1. Similarly, for a cloudy day, it is 0 plus 0.5 plus 0.5, it is 1. So
Hello,
this
Lavanya ma'am.
is what is the probability associated with the hidden states with respect to a man either wearing a short coat or an umbrella. Now we have to look into the transition probability.
Can you hear me?
Okay, the transition probability I'm going to represent using a red one dotted line. So from sunny to sunny, it is 0.8. Then from sunny to rainy, it is 0.15, and the transition from rainy to sunny, is 0.35. 1 minute.
Hello. Lavanya ma'am, can you hear me? There are just two people over there. You did not observe it? No, just Manasi and Funny Prashanti are there. No one else is there. You just see. One more is entering. Tulasi. Waiting in the lobby. But I don't think this. Okay, they are all in the lobby. 5 people are here. 7. When I was viewing, just 3 people were there. Just 2, and one more is myself and yourself. We'll continue and complete it. Fine.
Hello, how about others? They are not willing to come, is it? Is it that I am taking class for Sujata ma'am and Sujata ma'am for me? For this also no response? At least please answer. Huh?
We are not sure why they haven't joined.
Hey, 80 class to join பண்ணுங்க
Yes.
இருக்கும்னு நினைக்கிறேன் இல்லை அவங்க மேம் போட்டாங்களா இல்லையான்னு தெரியல பார்க்குறேன். சரிங்க நான் எடுக்கலம்மா இந்த தடவை கம்பைனாக அவங்க எடுத்தாங்க 3 செக்ஷனுக்கும் சேர்த்து இசி டிஇஹெச் ஜிஹெச் அந்த 4 செக்ஷனுக்கும் சேர்த்து ஃபெயிலியர்ஸ் கம்மியாக இருந்தாங்க.
What is happening now? Okay, we'll continue. What is your opinion? How about others? Shall we continue or not? Hello? You want a response? Are you able to follow?
Yes, ma'am.
Okay, then we'll continue. Right. Okay, so we have 3 hidden states: sunny, rainy, and cloudy. Now we are going to see the transition that is going to happen within the hidden states. So we were talking about the transition between sunny and rainy. Similarly, from cloudy, we have a transition to rainy. Here the probability is 0.05. From cloudy to cloudy, then similarly from sunny to cloudy is 0.05, sunny to cloudy is 0.05, and cloudy to sunny and cloudy to sunny is 0.75. Now, from cloudy we go to rainy, from rainy we don't have any arrow coming to cloudy. Now, how about the self-loop condition? So, sunny to sunny is 0.8, rainy to rainy is 0.6, and cloudy to cloudy is 0.2. So these are the probabilities which are given to us, and this particular diagram is known as a transition state diagram. It is known as a transition state diagram. Right. With this diagram, we can write 2 things. In order to proceed further, we also need to know the initial state probability. The initial state probability is given by 5. So your initial state probability is given by 5. Here 5 is equal to, what is your initial state? You have sunny, you have rainy, you have cloudy. So this is given by 0.75, 0.2 and 0.05. We see if you add this 0.75 plus 0.05 is 0.8. 0.8 plus 0.2 value is 1. Now with this diagram on hand, we are going to draw our transition probability matrix. We are going to draw our transition probability matrix. This only yesterday ma'am had illustrated while doing your Markov chain. So when you draw your transition probability, what do you have? Sunny, rainy, cloudy. So you have sunny, you have rainy, you have cloudy. Similarly, sunny, you have rainy, you have cloudy. The probability, sunny to sunny is 0.8, rainy to rainy is 0.6 and 0.2. So along the main diagonal, 0.8, 0.6 and 0.2. Then sunny to rainy is 0.15. Sunny to cloudy will be 0.05. Then rainy to sunny is 0.38. Rainy to cloudy is 0.02. Cloudy to sunny from the figure is cloudy to sunny is 0.75. Cloudy to rainy is 0.05. Cloudy to rainy is 0.05. So this is your transition matrix. Observe, it is a stochastic matrix. What do you mean by saying that it is a stochastic matrix? Row-wise, if you add, the row total of each row will be 1. That is the meaning. Okay. Now, this is a stochastic matrix. If column is also 1, it is known as a doubly stochastic. But however, here it is not a doubly stochastic. It is a stochastic matrix, that is your row total equal to 1. Now, how to draw an emission matrix? This is new. This is transition. How to draw an emission matrix? Your emission matrix is a connectivity which is going to run between your hidden states as well as your visible states. So you will start from sunny, rainy, or cloudy. And with what are you going to identify? Whether he's going to wear a shorts, or whether he is going to wear a coat, or whether he is going to wear an umbrella. So from sunny, wearing a short coat or umbrella is 0.6, 0.3, 0.1. It is shown in black in the figure. So it is 0.6, 0.3, 0.1. Similarly, for a cloudy, wearing shorts is 0, coat and umbrella is 0.5, 0.5. Next, for a rainy day, we have to consider for a rainy day, shorts is 0.05, coat 0.3, and 0.65. So you have 0.05, 0.30, and 0.65. This is how you construct your emission matrix. Is it clear for everybody? Your emission matrix is the one which relates both your emission states, that is what you are seeing, with the hidden state. Okay? And the transition probability is only between your sunny, rainy, cloudy. Only those three states are connected. You no longer go with what is emitted, that is wearing a short coat or an umbrella. Right? Is it okay for everybody?
Yes.
You are able to identify this. Next, we have to go into how to judge what is the type of state. So in HMM, so in HMM, we construct a model. We construct a model with three states. What are they? Your initial state probability 5 and A and B. One is transition probability and the other is emission probability. So here your 5 stands for your stationary probability. 5 stands for your stationary probability. Your A, it stands for transition probability, and your B, which stands for your emission probability. Once you have all these three things coming into play, how are we going to predict the hidden states? So given the observable states, what is my observable state? Can anybody tell me? Yes, can anybody tell me? Observable is what we are seeing, what the person is wearing. So, what is the observable state? Your observable state would be just, let us say, coat, and umbrella. I have left shorts at all. That means 2 times it's wearing coat, next time it's wearing an umbrella. With this sequel, I want to find out the hidden state. My problem is to find out hidden state. What is the hidden state? Can anybody tell me? Yes. Can anybody tell me what is the hidden state? Your hidden state is nothing but your weather condition. That is whether it is rainy, whether it is cloudy, or whether it is sunny. These three are your hidden states. Okay. So now we have to find total number of probabilities, maximum combination, what you will get. The total number of possibilities are n will be, let us take n to be the number of hidden states. Here in this case, hidden states is 3. Number of observation, P will be number of observation. How many observations we are making? That is also 3. So here our requirement m is nothing but n power t. So it is 3 cubed. So 27, which is high. Whichever value is high, whichever probability is high, that will be taken as the state, hidden state. Okay. So for this, we have to consider 27 such combos. Now look, let us take a first case. Let me analyze case 1. So I will have a hidden state and I will have an observable state. In the hidden state, I'm going to have sunny, I'm going to have rainy, and I'm going to have a cloudy state. Here, from sunny, let me say I'm able to see coat. That's what it says. Again, I'm having a coat. So from rainy also, I'm going to have a coat. From cloudy, again, I'm going to have an umbrella. Okay. Now, from sunny, I can go to rainy, and from rainy, I will go to cloudy. Now, I want to find the probability that he is wearing a coat and it is sunny. That is the first case. The first case, he is wearing a coat and it is sunny. So, because when I come to it, it is P of A restricted to U. Suppose he is wearing a coat and it is also sunny, it should be an intersection of both. So I will have coat, comma, sunny. So P of A as intersection B is P of A restricted to B into P of B. So P of coat restricted to sunny to sunny. So I have been restricting it as SU everywhere. So I will write it as SU. So coat restricted to SU into P of SU. Now, what is this? In general, you want to represent observable, comma, hidden. P of O, comma, Q is P of O restricted to Q into P of Q. This is the formula we will use. Suppose we want to take the complete set. How many? We are having 6 states. Sunny, rainy, cloudy, coat, coat, umbrella. So to take the complete set. So if we are to take the complete set, what all we will have? We need to find the probability of coat, coat, umbrella, and coat and sunny, or coat and rainy, or cloudy. So all these three also have to analyze with respect to this. So how am I going to get this? That is what I have to check. How can one find out this value? So this is nothing but we will take all the three and then start. He is wearing a coat and it is sunny. So this will be equal to, I'm writing the next line, probability he wears a coat and it is sunny. Next, he will wear a coat and it is raining. So probability of wearing a coat and it is raining. Then, what else can we take? I mean, probability of wearing a coat and it is raining. Then, probability that he is having an umbrella and it is going to be cloudy. So probability into probability of an umbrella and it is cloudy into, how should I multiply? Probability of your sunny into probability of this base, whatever it is, rainy, into probability of weather being cloudy. Suppose I write like this. Will it work out correctly? I'm having cloudy with respect to sunny. This is the starting condition. First thing what I'm observing. So it's the initial state. So I can write P of SU. It is correct. Now I'm telling he's wearing a coat and it is rainy. It is in the second condition. So what is the second condition? Coat and rainy. But before coat and rainy, what was it? It was sunny, correct? And then from sunny, it has changed to rainy. So you will have P of SU into P of RA restricted to SU. Now similarly, when you come for the next case, see here, it is having an umbrella. It is cloudy and he is having an umbrella. But when you are observing the umbrella, after seeing 2 times coat. So what was the previous case? Coat with a rainy day. So here what will happen? You will have probability of, finally you are finding cloudy day. Before the cloudy day, what was the state? Rainy day. After that, you are visualizing the cloudy day. So P of CL restricted to RA. P of CL restricted to RA. I repeat the process. When we get the complete set, we start first. I see a person wearing a coat and entering my room. So, okay, he is wearing a coat and it is a sunny day. So, it is a sunny day and the person is wearing a coat. Next, I observe a coat and it is raining. So, probability it is a rainy day and he is wearing a coat. Next, he is now taking an umbrella. It is cloudy and he is having an umbrella. Now all this has to occur. It should be cloudy, it should be again cloudy, you should wear coat 2 times, then an umbrella, and then sunny, rainy, cloudy. So you have to multiply it by the previous day condition. The first assumption is coat with a sunny day. So you will take the initial probability of it being sunny into the second instance of rainy and a cold. So before the rainy day, it was a sunny day. Hence, you multiply it with probability of RA restricted to SU. The third observation is taking an umbrella on a cloudy day. So before the cloudy day is the rainy day is equal. So you multiply it with probability of cloudy day restricted to rainy day. So this is how to get it. Now the first weather is independent. What is the first weather? Sunny weather. This weather is independent. It is not dependent on anything. So we take initial probability. So we take the initial probability P of it being sunny. Okay. Then you come here. Your rainy day. Your rainy day precedes a cloudy day. A rainy day precedes a cloudy day. Therefore, you take probability of CL restricted to RA. Right? Therefore, my total probability of CCU and SU, RA, and CL. This I have to write. I need the values of all these probabilities, for which I have to go to this matrix, from where I can get the probability. Now I want to take, look, sunny and he's wearing a coat with sunny is 0.3. So coat with sunny will be 0.3 into, what is the next thing? Coat with RA. My coat with RA, coat with RA rainy day, that is also 0.3. So I will come down, multiply it again with 0.3. Then what is the next feature that I require is an umbrella and a cloudy day. So that will be given by 0.5. Now please look, all these values I have taken only from the initial matrix. Okay, so The first three values we are taking from the emission matrix. The next values we have to now take for P of SU. P of SU I have to take from my P of SU I have to take from my pi value. Where is the pi value given? Initial probability. So P of SU I will be taking from here, that is 0.75, the initial value which we require. So into 0.75 into, I have to calculate RA into SU. RA into SU, I will come here, I go for RA and SU. That is, from SU, I have to go to RA. So I will be taking this 0.15. Okay, I will be taking from 0.15. Then again, similarly, we will get 0.02. So if you watch very carefully, this you will take from transition matrix, I think, and this you are going to take from your emission matrix. Am I correct? So this is how we calculate this value. Hence, if I need to find probability of an observing output from the existing hidden state, this value is nothing but phi, that is product of probability of OI restricted to QI into probability of, this is your transition matrix. So it would be QI restricted to QI minus 1. Yesterday you are dealing only with this portion. Today we are dealing with both portions. Okay, so this is what is the basic idea of your hidden Markov model. Now, once you get this value, now we considered one particular probability. Like this, we will have several probabilities. So we have several probabilities. Say how much in this case? P1 to P27. We have considered only one such probability. Say my P1, which is coat, and umbrella. Like this, you will have 27 such probability. Here we have considered for CCU, and CCU running from sunny, rainy, and cloudy. Okay, this is what I have considered in this. Okay, this is the thing which I have considered as P1. Like this, you will go on changing. So 3 cube base, you will get 27 such permutations, for each of which you will be able to calculate the probability of occurrence. Once you get this, our idea is to see which sequence occurs. Now, suppose today it is very cloudy. Will it rain tomorrow, or is it not going to rain and is it going to be anything else tomorrow? So how are we going to predict? For that, we use something called as Viterbi algorithm. Okay, so same Viterbi algorithm we will discuss now, and then we will go for our paper discussion. What does this Viterbi algorithm do? Let me simplify this. We have a hot condition and a cold condition. I'm sitting inside a room. I want to find out whether the person coming in, whether the temperature is hot or cold. So I am inside a closed area. I need to find whether it is hot or cold outside, based on the number of ice creams a person consumes. So eating the ice cream is only my emission matrix will contribute of both hot and cold as well as the number of ice creams. What I can see, only the number of ice creams that the person is eating. So that is the visible state. What is hidden? Hot or cold. So that is my hidden state. So now if I am to draw a diagram, I will have two hidden states. Hot, I will have cold. I'm going to have one ice cream, two ice cream, and three ice creams. So one ice cream, two ice cream, and three. This is what I will be seeing, what the person is eating. Let me fix the probabilities. 0.2, 0.4, and again 0.2. Then from hot to hot, it is 0.7. From hot to cold, it is 0.3. 0.7 plus 0.3 is 1. Again, from here, it is he's eating one ice cream. Let me take it as 0.5. He's eating two ice creams. Let me take it as 0.4. And he's eating three ice creams. Let me take it as 0.1. Something is wrong. What is wrong? Everywhere, see, 0.7 plus 0.3 is 1. 0.5, 0.4, 0.1 is 1. 0.2, 0.4, 0.2 is not 1. So that is an error. You should identify. So somewhere it should be 0.4. So let me take this as 0.4. So again total is 1. Okay. Now from cold to cold, let it be 0.6. So from cold to hot, it will be 0.4. That's what the total becomes 1. Right? So how are we going to talk about this model? When we want to talk about this model, we have observable state. How many states we are having, we have to consider. Now, in this particular case, we will calculate our M. So here, what happens? N denotes our hidden state value is 2, hot and cold. T, which is seen explicitly, that is 1, 2, 3 ice creams, so value is 3. Therefore, my total possibility M is n to the power t, and n to the power t is 2 cubed, value is equal to 8. Now, my initial state probability is given as 0.2 and 0.8 in the problem, and this is taken for hot and this is taken for cold. Then I want to write, they have to give the transition matrix and the emission matrix. I have to write from this figure. So let us now write our transition matrix. Your transition matrix is just going to be your hidden state consideration, hot, cold, and hot, cold. Here, hot to hot is 0.7, hot to cold is 0.3, the other one is 0.4 and 0.6. However, it's a stochastic matrix. Then you have to go for your emission matrix. I suppose you are gaining some familiarity with your transition matrix and your emission. In your emission visible states, you are having 3. Hidden states, you are having only 2, hot and cold. So for hot, it is 0.2, 0.4, 0.4. So it is 0.2, 0.4, 0.4. For cold, it was 0.5, 0.4, and 0.1. Now we have to discuss our literary algorithm for a particular sequence. So there are 8 possible combinations. How are they going to run? We are going to have boxes running like this, so denoting your hidden states. Maybe they will be ending up somewhere also with some hidden state. We don't know what it is. There are 8 different combos. Let me start with say CHH. Cold followed by 2 hot, hot. And visibility is he's eating 3 ice cream. Hot, he's eating 1 ice cream. Again for hot, but he's taking 3 ice creams. This is one combination we are doing. So we saw just now probability of O, Q, that is the observer, the hidden, is the argument max. That is the maximum value that you get, you must take from the product of P of OI restricted to QI into the probability of Qi restricted to Qi minus 1. This is the only extra step, choosing the argmax. That is the only step. But now, when does vitamin fail? For 3 and 3 cross 3, you run for 27. Imagine if it is 10 cross 10, that's it, 10 power 10 entries. But however, this could be programmed even using Excel, Java, Python, ready-made codes are available, so we don't have to worry. We will just look at a small illustration where we will be computing the probability. So let me consider a sequel where I'm going to have hot, hot, and then again I'm going to have a hot. And then I'm going to have cold, cold, cold. That is, there are only two states, either it could be hot or cold. So I'm taking first day hot, second day hot, third day hot. That is, I'm going to consider a sequence of length, 3. So the only option is either hot or cold. How it is going to happen? That is our idea. Okay. So here I represent it as 3, hot. Sequence of length 3 and I am starting with hot. Then here I consider a probability of 3, C. Now how we are going to calculate this? Okay. So now probability of 3, H is nothing but probability of 3 restricted to H into probability of H. So this is your emission probability. This is your emission probability, and this P of H is your initial probability because you are starting with this hot. Okay. So here, what is the initial probability? The initial probability for probability of it being hot is 0.8. I think this should be this and this should be. Probability of being hot is 0.8 and probability of H restricted to 3. Probability of H restricted to 3 is 0.4. So it is 0.4 into 0.8, value is 0.32. Similarly, probability of 3, C. This value is equal to probability of 3 restricted to C into probability of C, which is again initial probability. So here 3 restricted to C is 0.1 and the other probability is 0.4 and you have to look for this value. So it is 0.1 into 0.1 into. So this is 0.02. So now this is nothing but it is the Viterbi first phase value. Here it is 0.32 and here it is Viterbi first phase for cold. So I represent it as V1 of 2, which is 0.02. So it is V1 of 1 and V1 of 2. Now of this, you have to select the maximum. So the maximum selection, what we can give is 0.32. So we will be selecting this H as the 2. After this, we have to calculate the subsequent probabilities from H to H. From H to H. How do we calculate 1, H? The probability of 1, H. This is our P1 for which I have to calculate probability of 1, H. First transition H to H. So this is probability of 1, H into I can come from hot day to hot day itself. So this is my emission probability. This is my transition probability. Transition matrix I will do this value and emission matrix will be this value. 1H. So 1H value is given by 0.2 and H value is 0.7. So it is 0.2 into 0.7, 0.14. Okay, so here this value on the figure is 0.14. Then from H I have to go to C. From H I have to go to C. So how will I calculate P of 1 comma C? My P of 1 comma C would be 1 restricted to C into I'm going to cool from a hot condition. So I will come here 1 comma C is 0.5 into from hot to cold. From hot I am going to cold, value is 0.3. So this would be 0.15. So here my value is going to be 0.15. Next, I have to go from P of 1 comma H again. Where is this 1 comma H again? That is from C, I want to go to H. From C, I want to go to H. Let me denote it by P3, P1, P2. Okay, so this is my P1, this is my P2, and this is going to be my P3. Again, it is 1 comma H. That means with one transition, I go to hot, but this I'm going to go from cold. So it is 1 restricted to H into P of H restricted to C. So 1 restricted to H, 1 restricted to H is 0.2 into from C I'm going to H. From C going to H is 0.4. So into 0.4, which is 0.08. So this value will be 0.08. Similarly, I have to go from cold to cold. So I will go 1 comma C. So it is 1 restricted to C into cold from cold. So 1 restricted to C is 0.5, C to C is 0.6. So it is 0.5 into 0.6, which is 0.30. Let me call this as P4. So this is 0.30 and I am calling this as P4. Now let me proceed in the same manner. If I proceed in the same manner, I will be able to compute next V2. I found V1 of 1. I have to find V2 of 1. How to find this V2 of 1? So our V2 of 1, our V2 of 1 will be argmax. So it is maximum of 0.14 into 0.32. That is, I have to come here. I have to take this and multiply with V1. So 0.14 into 0.32. And the other one will be from V1 of 0.02 into 0.08. So it is V1 of 1. V1 of 1 into my P1 and V1 of 2 into P3. P1 of 2 into P2. So this value would be maximum of 0.14 into 0.32, comma 0.08 into 0.02. Obviously, it will be the first value. The first value is 0.048. So our V2 of 1 is 0.0. V2 of 1 is 0.048. Next, we have to find V2 of 2. How to find my V2 of 2? My V2 of 2 will now again be maximum of, I have to reach this stage either from hot or from cold. So V1 of 1 into P2, V1 of 1 into P2, comma V1 of 2 into 0.3 into V1 of 2 into this base one. What is it? P4. V1 of 2 into my P4. This value will be maximum of V1 of 1. 0.32 into 0.15. So it is 0.32 into 0.15, comma 0.3 into 0.02. Obviously, it is the first one. So my V2 of 2 will be equal to 0.048. V2 of 1 will be 0.448 and this will be 0.4. So here it is 0.448. Here it is 0.048. Now I should check which is bigger, 0.048 or 0.448. Obviously, the second one is bigger. So I will choose this and I will choose. So the sequence is hot followed by cold. This is how you start proceeding in a bitter tree. So similar fashion, if I have to go for the next phase, hidden to hidden, I will have this value to be 0.28 and here I will have my V3 of 1. If I calculate again before calculating, I should have hot to cold. Hot to cold is 0.03. Then I have cold to hot. I will have cold to hot. That also when I calculate it is 0.03. And cold to cold is 0.06. Then my V3 of 1 will be 0.0125. Similarly, my V3 of 2 would be 0.0028. So now I have to choose the maximum. H will be the maximum in this case. So this would be the maximum. So what is your sequel? I'm giving a double line. You will have hot, cold, hot. That is what is the hidden state. So the hidden states are hot, cold, and hot. So this is how your bitter D is used for determining the sequel of the hidden states. Now, okay, you went on telling hot, cold, hot. Why should I bother about the temperature? Right, you don't have to bother about temperature. Let us first bother about what we require, that is classification of images. This is a paper which has been published long before and it's very interesting on the basis of how they classify images based on hidden Markov model. I've just given you the reference in the first slide so that I owe my sincere thanks to the authors. So in their abstract, they propose to use hidden Markov to classify images. They are modeled by extracting the symbols corresponding to 3x3 binary neighborhood. So it would be 9 lattice points, and by ordering these symbols by decreasing the order and thus obtaining the strings of symbols. The HMMs are learned from the set of strings modeling the classes of images. The method is tested on a particular database which is known as simplicity database. Okay, it is available. From there, they have taken data. They also evaluate the approach by considering low resolution image and other methods. Now, how do they do that? In order to exploit saliency ordering, when they classify the images, they propose to statistically model the changes. So what they do, they consider them as observations associated to a chain of unknown or hidden states, like how we had hot and cold, which can be described as a HMM. The ordering of the symbols, the observations, is relevant and modeled indirectly through the ordering of the unknown hidden states. Okay, the meaning need not be known. Obviously, this hot, cold, and all we don't have to know. We only saw what he was running, and based on that, we decided. The hidden states are learned during the training phase. Now, how do they show this? See, the observable states they are giving O0, O1, O2, etc., On minus 1. The most salient key point. From the most salient to the less salient, they are arranged. This is how you saw in your Viterbi, right? That value, maximum value you went on selection. So this is the dependency graph of the hidden Markov model. The empty nodes are the hidden and the shaded nodes are what they see. That is the observable nodes. Now, this figure shows the dependency graph for an image with n interest point. We saw with 3 interest point and 2 interest point. Here it is n interest point. Each node corresponds to the variable where the observed variables are known as OI and they are given by the shaded circle. The uppercase letter denotes the random variable or the set of random variables. The lowercase letter shows the realization value from the random variable. Now we need the probability of observation, ith observation, to be some value small oi. This is abbreviated as P of oi. So using this notation, if we were to write it, how will we go about? Each image class is characterized by its own behavior. Therefore, each class is described by its own model. The difference between the two classes is of statistical nature and not the interaction between the observation themselves. Okay, it is the interaction between the set of why not to learn the hidden states and the production of the observation from the hidden state. That is what we did in Viterbi. Note that the hidden states are number of discrete values where the state space size is t. It is a user-defined parameter and the meaning is defined through the interaction. The value of the transition matrix gives this interaction and that is given by A equal to A K L. That is what we saw, cloudy to cloudy, cloudy to rainy, like that, right? The HMM learning algorithm tries to find the optimal description in terms of hidden states and the state transition probabilities producing the observed symbols. Now, the parameters for each of these classes, that is, you have two matrices and a vector. That is what first I wrote, phi, comma, A, comma, B, where A is transition matrix, B is emission matrix, phi was your initial probability, right? P naught. So C is phi KC, phi KLC, phi KTC transpose. The problem is a twofold problem. You have two phases. One is the training phase, the test phase. And then finally, the bomb-wedge variant of the expectation maximization algorithm and Viterbi are used. I illustrated Viterbi for you. I did not do EM for you, expectation maximization. Your expectation maximization and forward phase and backward phase, ready-made algorithms are available. You can just run your picture on those algorithms. Now let us look at a small example. So this is some example from the database, Simplicity Image Database. See how they have taken one crash, plane crash, and then you have a double decker, and then two horses going by, and then a natural scenery. The pictures are unique because you have three elephants, and then only one dino, one zoomed up rows, and then few number of horses with the background. So the pictures are all of different varieties. So consider these set of images. This result is obtained without using color information. Why? We are going to change them into binary, so it will be only grayscale. The images are binarized before extracting interest point, and we only consider the binary black and white 33 masks around each pixel. I suppose all these mask details we provided in the initial lectures of our course. Now see, you have two things. One is known as a confusion matrix, where you have the line X and column Y, which gives the number of images of the class X. So what are all the images that you have taken? And it has been classified in the class Y by HMM, Hidden Markov model, comprising of 50 states when using 4,000 points. Here A denotes the African people, that is what you are seeing. A denotes an African people. B denotes buses, C denotes horses, D dinosaur, E elephant, F flower, G is mountain, H is building, I beaches, and J is food. Okay, so with this only we are going to categorize this. Based on the pixel, you are getting all these entries in your matrix. For with these values, with this we are calculating an HMM. How many HMM of 1, 2, 5, and so on. When they do this, we have reduced all the images from their original size 384, 256 pixel to 128, that is roughly one third. You divide 384 by 3, you will get 128. Similarly, 256 by 3, roughly 86 pixels. For these thumbnail images, we have only extracted the 1000 first salient points. This table 3 shows that it is not really relevant to integrate the ordering. Not necessary because the values are all less high, less, it's all scattered. Better results are obtained with smaller number of states on HMM. The author is still able to correctly classify 61.6% of the images with HMM of 1. Number of states is less, the classification seems to be better. Then, this is how it is being used. HMM is being used in your images. So what we are doing, we have taken set of images. Having taken all the set of images, we are going to denote them by grayscale, black and white picture. When you denote it by black and white picture, you are going to develop a 33 mask. Once you develop the mask, what happens? You are going to get the values which you are going to take here. Once you take all the matrix in the confusion matrix, you denote all these values. Using this, you apply the Viterbi algorithm and try the sequel. You try to see if you are able to identify the object. They say up to 61% it is coming correctly with thumbnail images with HMM of. So this is a very vague idea which we have presented today. But however, that is why we thought immediately instead of going for a paper, we will illustrate it using simple 3-state HMM with I would say cloudy, rainy, sunny, indirectly inbuilt condition, which person recognizes by seeing what the outsider brings inside a room. And then we saw what is a transition matrix and how to construct the emission matrix, how to find the probability, and then given a sequel of particular length. For example, here we considered of length 3, and then we applied Viterbi algorithm, and we were able to find out what was the state of temperature outside and like hot, cold, what we derived. And then we just took a paper and we just went an outline of the paper and saw how HMM is applied to that paper. Okay, so I think you would have got some idea like what we are teaching for the past 2 days is more relevant to your subject and it is not out of the way. There are only 10 people in the meeting. So let me note down their names. I think that will be better. Just a minute. Okay. We have Bhuvi. Then we have Jaspion.
Yes, ma'am.
Then we have Manasvi,
Yes, ma'am.
Pani Prashanti,
Yes, ma'am.
Rashmi Kumari,
Yes, ma'am.
Shreyas?
Yes, ma'am.
Shreyas? Um,
Present.
okay. Then Sunil Singh?
Ma'am, it's Sahil. Sahil. Sahil, sir.
Sahil Singh. Yes, I remember Sahil.
Yes, ma'am.
Then Tulasi Nagi Reddy. That's it. Yogesh Kimari. Yogesh Kimari is there? No. So I think you'll be able to follow what has been discussed today. Your hidden Markov model will take you a long way in modeling images. It is used widely in image segmentation and in obtaining clarity of images also. So all those things in detail, I suppose Sheila ma'am's lecture will be taking you on to your subject. So this is the mathematical aspect which we wanted to share with you regarding HM. Thank you and all the best for your upcoming cities.